afternoon. So last time we talked about the determinant of a 2 by 2 matrix. This is like this checksum calculation that you can do for a matrix, a single scalar value that you get by doing these two numbers multiplied together, subtract those two numbers multiplied together. And then I did encourage you to go away and look at how you can do it for a 3 by 3 matrix, which is this really odd sort of formula where you basically sort of work out the determinant of that matrix and multiply it by that number, and then you work out the determinant of the matrix you get by taking those two and those two, multiply it by that, and then we do the determinant of those two multiplied by that. And do you know what? There is a formula book for this course. As soon as it has anything useful in it, I'll give it to you. It's not in there. It's not in there. I felt sure it would be, but there we go. So because the good news is that your calculator will do this for you, won't it? So should we just, using my completely made up matrix, let's try and work out the determinant manually, and then see if you can remember how to enter it on your calculator and get the calculator to confirm whether or not you've got the right answer. Okay? So that was in the textbook on page 100 and something. Using that made up matrix. I'm going to do the same. Oh. I get 106 manually and 105 on my calculator.
I've got -105.
You got 105?
-105%.
Minus 105, yeah. I get minus 65 plus 7 minus 48.
Say is that?
Is that what you got?
-65 plus 8 minus 48.
Oh, plus 8. Oh, no, I've got 0 times 1 is 0, isn't it?
Yeah. Oh, wait. What thing of mine?
So there you go. No, you're right. Yeah. Yes, it's minus 105. Thank goodness. Thank goodness. Yes.
When I put the 2 by 2 determinant thing in my
Wait, what's
this
this?
-500.
Well, you don't need to do the 2. You can do it the 3 by 3 on your calculator.
Yeah.
So you don't need to do it this way. So when you use your calculator, you can just go straight to type in a 3 by 3, and let me see if I can. Right, so I need to go to there. So I've entered that matrix as a 3 by 3, and then it's really rubbish, isn't it? Exit, and then option, matrix, and then I just did determinant of matrix A, and it gives me the matrix A in one go. That's the good news, is you apart from missing value questions, you can always get your calculator to work out the determinant of a bigger matrix, 3 by 3, or even bigger. Is that okay, Tristan?
Yeah.
Yeah, thanks. Can I just remind you of a couple of terms that cropped up, which are crucial for what we're going to do today. Those are, if the determinant is 0, then the matrix is referred to as singular. So yeah, I'm a big fan of Sherlock Holmes, and if you read Sherlock Holmes, he regularly refers to things as singular, which means sort of, unusual, exceptional, one-offs. That's not what this means in this case. And another thing, which isn't related to the determinant, but that we talked about the matrix I, which is referred to as the identity matrix, which is a matrix which has this pattern of 1. So that's the 2 by 2 identity matrix, and you can have a bigger one or a smaller one. And it's quite interesting just to think about if we use the matrix multiplication technique that we used last week, and we multiply a matrix by the identity matrix, it has no effect. Do you remember how we do it? So you do 3 times 1 and 4 times nothing, and then 3 times nothing and 4 times 1. So this is sort of the matrix equivalent of 1. 1 times a number gives you that number. Well, the identity matrix times another matrix, provided they are conformable, multiplicatively conformable, what is it? I forget now. That has the same effect. And I want to make those 2 points because today we're going to talk about inverse matrices, I'm hoping that by the end of today we can actually use matrices for something practical and actually do some sums with them. We're going to stick with 2 by 2 today because, unsurprisingly, 3 by 3 is really, really complicated, but we do need to do it. So the inverse of a 2 by 2 matrix, that's what we're looking at today. So let's imagine that we have some 2 by 2 matrix M. Then the inverse of that matrix is signified by the notation m to minus 1. That's, that's for a change is what we perhaps would expect. We used that notation when we were talking about functions at GCSE. And the inverse of a function is such that, get it the right way around, if you take m and you multiply it by its inverse, you get the identity matrix. Okay? So it's a little bit like saying, if you take 2, what do you need to multiply it by to make 1? In that case, it's the reciprocal, isn't it? You take 2 and you multiply it by a half, and you get 1. Well, in the matrix world, if you want to get 1, the identity matrix, what do I need to multiply my matrix by? That's what the inverse is. And the definition of an inverse, which is not on the formula sheet, and I'm already taking colour for what Jack's going to say now. So the definition of the inverse is 1 over the determinant of n, which sometimes uses that modulus notation, doesn't it? Multiplied by a rearranged version of the original. So you swap your A and D and you change the sign of B and C. But there is a sort of purpose here. There is a sort of purpose. So, it's hopefully beginning to make a little bit of sense by the end of today. Let me just get that out of the way. Hang on a minute. Get that out of the way.
Yeah, that's what I'm saying.
Now, could anyone suggest a situation where we wouldn't be able to calculate this? What sort of matrix isn't going to have an inverse?
Determinant is singular, or if the matrix is singular.
If you've got a singular matrix. If the determinant is 0, you can't define its inverse. You can't define its inverse. So, that's worth commenting on now, because if you have a determinant of 0, there's no way we can proceed any further. So there's 2 things we need to do, isn't there, in order to calculate the inverse. We need to do the switching around, and we need to calculate the determinant. Do the determinant first, because if the determinant is 0, we're wasting our time. So let's just do a little check that we can do this. So you've got 3 2 by 2 matrices here. So for each one, we're asked to decide whether or not they are singular. So that means work out their determinant. Remember, the determinant is just those 2 numbers, take away those 2 numbers. Product of those 2 numbers, take away the product of those 2 numbers. And if it is not singular, can you define the inverse? Yes.
Do you want to the determinant by this and that?
Yes. So you've entered your matrix,
Yeah.
then press Option. Oh, hang on a minute. Oh no, you've got matrix A, right? So you might press Option, and then it's that button there, and then it's there. So you go determinant of matrix A. Right, option.
That's quite far.
It's, well, I mean, it's the calculators are not user friendly, really. Are they? Yes.
Does it matter, like, once you've found out one of the 10, does it matter when you expand?
No, it doesn't. However, I'm going to write it in the the fifths form, because what we're going to do in a minute is just to check that when you multiply the matrix by its inverse, you do get the identity matrix. So
Well, you need to put into your thing first.
Do we just have to remember the weird, like, rearranged thing? For the,
yeah, it does seem unfair, doesn't it? Yeah.
Are we meant to remember that, are we?
Yes.
Oh god.
Yeah. It's, yeah, no, I'm not hiding the formula sheet from you, but I had a look at it yesterday. It's completely useless. So you get determinant of A is 5, so the inverse is 1/5 times those two swapped. They're already swapped and those two swapped. I don't like that. I wrote it as 1/5, 2/5, minus 2/5, 1/5 and 3/5. B is singular, so we were wasting our time there. There's no inverse that can be found. C, the determinant was 1 minus a sixth, that was 1 over a sixth. Oh, and this one they wrote as fraction, which is much, much better. Now remember, the definition of the inverse was that it was the matrix such that when you multiply the original matrix by its inverse, you got the identity matrix. So should we just try that for A? So if we go back to the question, A was 3, 2, minus 1, 1. So let's just try multiplying that by its inverse, which is 1/5 minus 2/5, 1/5, 3/5. And do you remember how we multiply? So those two multiplied by those, add them together. Those two multiplied by those two multiplied by those two multiplied by those, and that gives us, in this case, a 2 by 2 matrix, which we are hoping, fingers crossed, will be the identity matrix. And the other thing, do you remember we said that matrix multiplication wasn't commutative? Got a different answer if you did it the other way around. So just see what happens when you do this one the other way around. So this one you get 3/5 plus 2/5, which is 1. You get minus 6/5 plus 6/5. You get minus a fifth plus a fifth, and you get 2/5 plus 3/5. So that does work that way around. What about the other way around? Do we have a conclusion? Do we get an identity matrix the other way around? So it's interesting, isn't it, that this is an example where where we are commutative. Now don't ask me if it's the only example where matrix multiplication is commutative, but it certainly is. So we know that with our inverse definition, that equals I, but so does that. And that's a key result. Right, now let's build up. I did promise you that by the end of today I'd hope we could use this for something useful. So let's do. This doesn't seem very useful. Okay, this doesn't seem very useful. I will give you this much. But this is the sort of question that appears to sort of crop up. So A and B are matrices, C is a matrix, and we are being asked to, in some way, write an expression for B in terms of A and C. Now we can't just do this. That doesn't work with matrices. The rule we've already seen, the rules for matrices are different. For example, commutativity. You can't say that two things multiply together. But instead, we can do quite a neat trick. If I multiply both sides by the inverse of A, what does that mean I can now do? What can I now say? What can I now say, Ethan, about the left-hand side?
You just cancel out the A and B, A minus 1.
Yeah, this equals the identity matrix, doesn't it? And we know that when you multiply something by the identity matrix, you just get that something. And we tested that right at the very start. So this is what, now you might say, well, that's not in terms of A and C. Well, it is. It is. So what we can now do is we can now find B because we're given A and C. So go on, just see if you can find the inverse of A using the process we've just been through and multiply it by C. Yes?
How do you know which side that the inverse of A, or does it not matter?
Oh, that's a really good question, isn't it? Why did I... Well, on the left it didn't matter, did it? On the left it didn't matter. Yeah, yes, I must have, I never thought of it like that. I guess it is because, yeah, if we're putting it in front on the left-hand side, I guess we have to put it on front on the right-hand side, but I'm just trying to think, what's the justification for that? Yeah, no, that's, yeah, I haven't got a good answer for that one. I'm not going to blag it and pretend I do. But certainly, consistently, that's what we do. That's what we do, and we'll see how I'm going to sort of apply this in just a minute. Hopefully, yeah, we should just about make it. always feel that I'm rushing you, and I'm sorry about that. I'm cheating desperately by using the solution bank here. So the inverse is like that. I'm interested to note that they chose not to multiply that out this time. That was the question you asked, Tristan. So you end up with that. So if you haven't finished that, why not make a note of the answer? And I'm really keen to do so. Just, if nothing else, to try and justify to Jack that there is some use. There is some use in this.
How on earth could this be used?
It's
So random.
I mean, it has two main uses. One is in graphics, and we're shortly going to come on to looking at its use in sort of more dynamic, animation rather than just sort of static storing of pictures. But the other is solving sets of equations. So, okay, let's go back to a simple set of simultaneous equations. All right. Now, we're starting with something we can already do. All I want you to imagine as we do this is the way that this is extendable, scalable. So a similar method, albeit a slightly more complicated method, could be used to solve a much bigger set of simultaneous equations. At the moment, we can solve sets of simultaneous equations with 2 missing values, but we can't if there are 3 missing values, or 4 missing values, or 5 missing values. But are you happy that if I wrote this, and multiplied it out, I'd get that, wouldn't I? Okay, so that and that, it would give me that. So now that's a little bit different to the way I've represented a set of equations a week ago, if you remember, and I was trying to justify our use of matrices. And in that one we sort of used what I would describe as row operations to solve it, but this is a little bit different. So what we're effectively saying here is some matrix multiplied by xy gives you some other matrix. All right? And what I want to know is, what does xy equal? I want to know what x is, and I want to know what y is. So we can do our really neat trick. We can say, right, okay, let's multiply both sides by the inverse matrix. And what that means is on this side, you just get xy. It sort of cancels it out. And so the answer to this problem is just the inverse of that matrix multiplied by v. So go on, see if you can define the inverse of that matrix. See if you can multiply it by v, 16 minus 1. We know we can solve this, and in fact at A-level we don't need to because our calculator solves it. My point is, can you see how this could potentially be scalable to a set of 3 equations, 4 equations, 5 equations? Yes.
Right. So you know like the -7 all part? Can you
Yes.
ignore that and then divide it after?
Yes, you can. You can.
Right, so there's
Yeah, we should get the same answer. So you should get 2 and 5. I chose to multiply it out first.
Yeah.
But if you chose to do that times that and then multiply it by 1/7, yeah, I'm not sure there's a better way of doing it. Now my working there is dreadful. I've worked out the inverse function as that. And then, so I'm going to rub out the red, so because that's bad maths. And then when I multiply that out as I just did there, I got 14/7, which is 2, and I got 35/7, which is 5. So what that tells me is that x is 2 and y is 5. Now, you know, that is not a complicated, we'd be crazy if we used that method to solve these simultaneous equations, because we've got all manner of other methods up our sleeves to do it, not least whacking it into the calculator. But can you see how it's not a huge stretch to scale that up to a 3x3 matrix? It does require the determinant of a 3x3 matrix, which we already know is complicated, except we can do that on our calculator. And it does require the inverse of a 3x3 matrix. And that's one of the 3 things I think it would be worth looking at before Thursday. So if I find in the book where it does that, and it says something hilarious like the inverse of a 3x3 matrix is more complicated. There you go. Yes, so that's on page 112. And it requires, yeah, have a look at it, have a look at it. The only thing is, please now, whenever you are working out the determinant, use the calculator to do it for you, all right? And by that I mean, because you've got all manner of determinants going on there in order to find the inverse matrix. If someone can find, I'm surprised the calculator doesn't do it. I can't work out how to get the calculator to tell me the inverse of a matrix. So whether I'm missing some obvious function or whether that's just one of those things it doesn't do, I don't know. So that's but I'm sort of hoping you can see where we're going with this in terms of solving equations. And once we can do the inverse of a 3x3 matrix, we can do the last bit of this particular chunk of matrices, which is solving a set of equations which at the moment we can't solve. So, you know, this is where we want to go with this. At the moment, if you've got a system of equations like this one with 3 missing values, which requires to have 3 equations in order to solve it, we can't do it at the moment. I'm hoping that we can get to the point where we can do that using matrices. Sorry, yes?
Apparently you just put in the matrix to the power of -1, it doesn't.
You're a genius. Whoever told you that is a genius. Does that work?
Yeah.
Fantastic. That's just made my day. So if I go, do I go matrix
And then, then the matrix to the power of -1.
A? Right, so I need to go away and check my syllabus to make sure to see what method is. It's worth having a look at page 112. But yeah, I need to go away and just double check then what we're expected to do manually. And I've got a really clear view of what we can do manually at A level, and in case that hasn't been made clear to you, you can solve quadratic equations, you can solve 2 variable simultaneous equations, but other things have to be done, and then just use your calculator to sort of confirm it and check it. So, but now we can do this. We could straight away. We won't. But we could straight away now solve that set of equations. In fact, some of you might want to go away and have a go. You know, it's quite fun.